Alright, hell yeah. So we're going to go over Mohr's circle. This is material mechanics gear. This is probably one of the hardest. This is kind of make or break in this book, where you're just like, nope, I have officially thrown in the towel. This is not for me. Too much going on. You know what I mean? One, before you get to Mohr's circle, you have all these equations, the transformation equations, and there are just too many of them. And so what I'm going to do in this video is kind of like a who cares perspective. And so, you know what I mean? One thing in material mechanics, I never liked this little square. You know what I mean? It seemed confusing. But, you know what I mean? Hey, we're going to like pull some tension on something. We can understand this because maybe I have a steel bar. And I always use kind of like a 1-inch steel bar. Because, hey, we could pull on it this way. Cool. And if I maybe shorten this steel bar up, maybe I would be able to pull on it this way and kind of compress it at the same time. You know what I mean? That way. So maybe I have two things going on. And cool. And then maybe while I'm doing that, I'm also, and maybe this is like if this was a beam, maybe this is a distributed load, you know, on both sides, however you would do that. You know, but that's why we have this, you know, this maybe compressive force over this entire surface area there, and then on the bottom surface there. Same thing here on the sides, you know, I mean, we're going to be pulling a tension, and that's going to act that way. I'm just trying to get into the fact of like how do we show a shear force? Well, maybe, you know, I mean, we still have this little chunk of 1-inch steel, but we want to rip it apart. And so what we would do, let's say we wanted to rip it apart this way, and so we would put a downward force there, and then a downward force there. And so what happens is that if we kind of take a little element, and we don't even need to take, you know what I mean? If this is our bar and we're doing that there, I mean, we could just take a square element there and just say, hey, now we're just going to take a big chunk, a cube, and guess what? We're going to have, on this face, we're going to have this downward force, essentially, and then on this other face, the opposite face, we're going to have a force. And so, cool. And then so, you know, previous chapters up to this point, you know, I mean, we say, hey, these two forces, and if we looked at this, if this bar is actually going to deform, where it's starting to do that, and then break in two. I kind of drew it wrong, but anyway, yeah, there you go. So as it's, yeah, I still kind of drew it wrong. But anyway, so as this thing is breaking in two, you know what I mean, this little cube now looks like this. And so it turns into a diamond shape. And so cool. So on our picture, we would say, hey, this would turn into a diamond. And if it turns into, and so let's switch this around, just because we want to show positive shear. And positive, you know, in a free body diagram when we're doing beams, hey, if we throw the loads on like this, it's going to cause this thing to rotate counterclockwise. Which right-hand rule, that's positive. But when it comes to like, hey, if we're trying to find the shear, we would call this a negative shear. And that's kind of a bummer. Just to, you know, because the sign conventions seem to be like all over the place. This video, I'm not going to go into that. But when it comes to these diagrams, so if we have this upward force here, so we're going to have an upward force and a downward force, you know what I mean? And it's going to cause this thing to turn into a diamond shape like that. And so on our diagram, that's going to be an arrow up. And this diagram is in like pressure. It's in PSI, or it's in pascals, which is Newton per meter squared. PSI is pounds per inch squared. And so these are the pressures on, so if we do have a cube, so this is a cube. And so if we do have a cube, we're saying that there's pressures on the faces of these cubes. So on this face, there's going to be a normal pressure that's associated with this force. So I know if this was a free body diagram, I know this force is the pressure, which we're calling sigma, times the area. So that's going to be like newtons per meter squared times meters squared, and then we get a force. And so on our stress diagram, and we can make it three-dimensional, I'm going to say on this surface, I'm going to have a pressure that's going to cause, that's associated with this tension. You know, I mean, you can imagine tension maybe taking something and putting it into the vacuum of space. It's going to be pulled apart, let's say. And so hell yeah. So this is going to be the pressure on this face, and we're going to call this the x direction. And so, cool. So same thing here. This is the y direction, and this is associated with a pressure on the y. Now, if we get something that wants to make it turn into a diamond shape, that means this is kind of, you know, it's like sideways pressure. So it doesn't fit into the scope of of fluid mechanics, of what we consider like a, you know, compressive pressure and then vacuum pressure, you know, like normal pressures. But it's we still say there's a force that's, you know, theoretically on this surface, and so we could be like, hey, there is a pressure here, and so that pressure, so we would have, and this is tau xy. Now the sign convention on this is if this is on the positive x face and this pressure is in the positive y direction, we're going to call this a positive shear pressure. Cool. This is associated, again, with a positive force. And so free body diagram-wise, if I have a positive force in this direction, on this other face, I must have to have an equal and opposite. Because that's the only face that I can have a vertical force due to that shear. Because if I can have shear on this face, but it's just going to be horizontal. So if I designate this, I mean, this is kind of the first one you're trying to find. If I designate this, then I know that this is associated with a force, and that force is going to cause this element to rotate that way. Well, two things. One is this force is in that direction. And we know this thing's not traveling in that direction, so equal and opposite, we need this same force over here. It's acting on the same area. So we can also say the stress over here is down, and it is equal to this, tau xy. Now, on the top surface, we're going to have, so this is going to cause a rotation this way. We need to balance it with a force, at least one force that way, you know what I mean, to kind of balance this rotation. And if we include this horizontal force, now our forces are unbalanced. We need to include a horizontal force down here. These two forces are separated by a distance. These two forces are separated by the same distance. So therefore, these two forces generate a torque or a moment, and these two forces counteract that equally. And so this force would be equal to, you know, these two forces would be equal to those two. So therefore, the stresses are the same too, because these forces are acting over an area. So we have, let's say, stress is force times area, and then so we can go, and I just solve for force. So I have force, and I want to find stress. Well, I just spelled it out. Sometimes you're just like, maybe I know the stress, but I want to find the force. So if I know the stress, I would divide by the area to find the force on that, you know, kind of side. But here, if this is a force diagram, hey, I know this force, and it's acting over that area, so therefore that's the shear. And it's going to be the same as that. Now we designate, so it's going to be an arrow this way. And we could just say it's, right away, we could just say it's the same, tau xy, because we're going to say it's the same anyway. But to designate this, we're going to say this is the shear on the y face, and it's on the y, this face is pointing in the y direction, and the shear is in the positive x. And that is the definition of positive shear. If it's on a positive face, and then in a positive direction. Cool. And then so we have this down there. And this is on a negative face, but it's on the negative direction, so negative, you know what I mean, kind of, that's still a positive. This is still, all of these are positive shear forces. Alright, hell yeah. So that was a pretty good introduction. I really didn't even want to do that. I just wanted to go over, you know, some of the basics of the Mohr's circle. So, but this is, what we're given is like, hey, you're given a problem where you have sigma x, you know what I mean, sigma y, and then some sort of shear. And, you know, just from your whatever, you know what I mean, you're trying to load something, pull on something, push on something, and shear something at the same time. Beams are that way. You know, you got all three things going on. And one of the aspects of material mechanics are this pressure. Like, a material can only withstand a certain number for pressure. You know what I mean? In tension, for steel, it's 58,000 psi. For compression, it's 58,000 psi. In shear, it's half that, 29,000. So if all you know from material mechanics is the fact that a material can only take a certain number, and it can take it in tension, compression, and shear. So these are your normal forces, and then these would be your shear forces associated with. But the pressure, you know what I mean? So if I have 1 inch of material, hell yeah, for steel I could take 58,000 pounds. If I only had half of that area, I could only take 29,000 pounds in tension, but the pressure is the same. The pressure is force divided by area, so we would have 58,000 divided by 1. This area would be 29,000 divided by a half, you know, this is 1 inch squared of area. This would be 1 by half. This would be ½ inch squared of area. So the pressures would be the same. They'd be that 58,000. So that's the take-home point. So the general gist, especially when you're getting into the weeds of material mechanics and you're just like, hey, this is hella confusing, or just like, you know, too much to handle. Basically, at the end of the day, it's just like, hey, you just can't exceed that number. You know what I mean? So that keeps it kind of basic, even though you can get into, I would love to try to get into like PhD material mechanics of seeing kind of what's going on at molecular levels and just kind of all the, because like even as complicated as this book is, it's just one assumption after assumption after an assumption. You know what I mean? You do your best. It's mainly geometry, and you know, and there's, you know, from the assumptions, there's still quite a few special cases, and so you kind of you go from broad brush assumptions to, hey, maybe kind of you know, kind of cornering the market on some of these different designs. But in general, hell yeah, a material cannot have a pressure at any point bigger than that number. If you do, you probably have problems. You know what I mean? Some things are designed to actually, you know, indeterminate things are designed to be like, okay, we're fine if that reaches that pressure, but other things are going to carry the load. But just in general, hell no. You know what I mean? You want these to be, your pressure, you know, factor of safety of 2, just make sure you come up with numbers that are a half, you know, just on all those. So if you're kind of designing something, yeah, and so that rounds it out, because that is now a good introduction for Mohr's circle. Because what we do is, it's really easy from our analysis to be like, oh, okay, it looks like I'm tensioning something, I'm compressing something, and maybe I'm shearing something. So I get those 3 numbers. So these are the 3 numbers that I'm given. But what happens, and that's why chapter 2 says, like, hey, look at this. If I'm tensioning something, and this is going to be biaxial stress, everything's got crazy definitions. I don't mind them, you know what I mean? But I just kind of like the concepts first. So if I'm tensioning something, like that steel bar, what happens is it actually fails at a 45. You know what I mean? It could it could just, these molecules could just pull apart like this. But they actually don't. And one way to think about this is, like, let's say you have two pieces of steel, and you put them together like this with double-sided tape. So steel is hella strong, and then you, put double-sided tape, and then tape those two things together, and then pulled in tension. What do you think is going to happen? Do you think it's going to rip down the middle? Hell no. You know what I mean? It's going to slide across that surface, and that's going to be a failure in shear. So that's probably the easiest and obvious way to see, like, oh, yeah, things can fail at angles, but in this case, that angle was a weak spot. Well, steel has a weak spot. Steel can't take shear forces very well. And just that number's half. So that's all you have to know is just like, hell yeah, that number's half. And then so what we do is and let's see if I can actually kick this one out. So if we have a 45, we have this tension. Now this tension is an arrow, and I have to have that same arrow on this side. But if I opened up this face, I'm going to have two components. I'm going to have a normal component and then a shear component in this direction. And so, parallelogram theory of adding vectors is I have to go here and then here. And so I'm going to have a normal force, that direction, and then a shear force, that's this direction. Now these are smaller, so let's try to get this to scale. So that arrow is my tension, and that's the same thing as here. And to get this length, I'm going to go a normal and then a shear. And then these, because it's 45, cosine 45 is 0.707. That's square root 2 divided by 2. And how you know that? The square root 2 is 1.414. And, ooh, look at that, 77. Booyah. So it's 0.707. Do you see that? Divide by 2. Hell yeah. Alright, hell yeah. Sometimes my camera cuts out, so we went through here. And so I did say, hey, this is square root 2 divided by 2. And square root 2 is 1.414. And so, hell yeah, if you divide this by 2, see how this is 14 and 14? You get 0.707. You know what I mean? So that's kind of, it's good. I just memorized this, but then after a while I was just like, well, why am I memorizing this? And where the hell does it come from? Well, it's halving square root 2. And I know square root 2 is 1.414. It's actually 1.4142. And so this is really accurate to 3, because if I divide this, and I even messed, it's 0.7071 maybe. Cool. Hell yeah. But the take-home point is it's 70%. So if I tension this, 70% is going to be in this normal force, and 70% is going to be in the shear force. And that's significant. And so let's go back to talking about what we're tensioning this bar with. 58,000 pounds. We said it's steel, and we said that's when steel will rip apart, or that's like the max tension steel can take. And so then I came down here, and I was just like, well, let's talk about, because this shear stress seems significant. It's 70% of 58,000. You know what I mean? So that should ring alarm bells, because let's say I just took this 58,000. I mean, if I have the capacity to pull on something with 58,000 pounds, it seems like I have the capacity to do this with 58,000. So that's what we're going to do. We're going to take this steel bar, and we're going to do this with it, and we're going to do that 58,000 pounds. And so this tension is going to be, used in shear. And guess what? That shear force is going to try to rip apart across this surface. And with this being 1 inch by 1 inch, the area is 1 inch squared. The force is 58,000 pounds. So the pressure, the stress in PSI, or the stress and pressure on that surface, is going to be 58,000 PSI. And what did we say that steel can take in shear? 29,000. So this is going to be twice as too much. It's too much, you know what I mean? So you would only be able to put a force of 29,000 pounds. And so just the fact that, hey, we have came up with a shear force that's going to be 70% of this. And can I do that on the spot? Probably not. 58 times 7. Let's just do it that way. 5, 6. Is that right? 5, 6, 7, 8. 35, 40. And so, yeah, we're going to get 40,600 pounds in shear, which seems bigger than 29,000. So then what gives? Well, this shear force is this shear force is pulling over a larger surface area. So the surface area grew to 1.4 or the square root 2 times 1 inch squared. You know what I mean? If the cross-sectional cut was 1 inch squared. Alright, we got some more juice in the camera. And yeah, so what happens with this is that we have a shear force of 40,600 pounds, which is the same thing as 58,000 times the square root 2 divided by 2, so keep that in mind. And if you derationalize this, you would multiply top and bottom by the square root 2, and then so this would be 2 cancels 2, so this is just 58,000 divided by the square root 2. So that's going to be the shear force, and it's going to operate on an area of square root 2 inches squared. And then so the shear pressure is force divided by area. You know what I mean? Pressure just in general. And it's always good to do this. You know what I mean? Just pick a unit on pressure. That's going to be newtons per meter squared. I've been trying to get better also at just using the first chapter stuff as being like, hey, this is a force and this is a length squared. And so if I want to, if I know a force and I know a length squared, which is area, then I know the pressure. So I can easily see now that this is the shear force divided by area, and we're good to go on this equation. So the shear pressure, and then again, the take-home point is we just want a number on that pressure, that shear stress. They're calling it stress, you know what I mean? And shear pressure, shear stress. So if I get a number that's bigger than 29,000, I got issues. And so let's see what we get. So we're going to get a, so, you know what I mean, drum roll please. And so we have tau is equal to this force, 58,000 divided by the square root 2. And our area is now the square root 2. I feel like I did something wrong. Oh, that's cool. So I turned off the camera for about 3 seconds. You know, I talk about that. This came up from a commenter. It's like, how do you record stuff and then just, when you get into like some sort of fogginess or just like a brick wall, even just right here, I was going to make an algebraic mistake. I was just going to take this to the top. And I mentioned that. Like, I swear, even if I just had like 1/2 divided by 2, for whatever reason, this came up in the quadratic equation, and I just think this is 1/2 times 2. You know what I mean? It just seems like, oh, I got something downstairs. Can't I just, you know, well, you got to invert it. You can bring it upstairs, but you got to invert it. You know what I mean? So, so hell yeah. So if I bring this upstairs, I still got to invert it, and then we have 58,000 divided by 2. Because I was just like, I thought these were going to cancel, and I was just like, hell no. So what we get is, you know, if I'm going to bring that upstairs, I better invert it. And so now this jives. This becomes 2. So I have 58,000 divided by 2. And now, drum roll, the pressure is 29,000. And we just said that steel can fail at 29,000. Basically half of what it would in the amount of compression or tension steel can take. So it's... And this is like, so this shows that this number is not bigger. This number didn't come out bigger than 29,000, but it did come out 29,000. So you can say that steel has an equal likelihood to fail in planes of shear. You know what I mean? Just like you had 2 chunks of steel that you cut that look like that, and then you double-sided tape them together. And that double-sided tape could just take a pressure of 29,000. So that's a good way to think of it. Just anytime that you have a steel bar, just pretend like on 45-degree cuts, just pretend like it is cut and then fused back together with a material like double-sided tape that, I don't know, and very strong double-sided tape, but half as strong as the actual steel can take in tension. So that's kind of a good way to look at it. So yeah, equally likely to fail in shear as it would just these molecules just tearing apart and ripping apart. Okay, so that covers it. And I guess, we haven't even talked about Mohr's circle. So this would be an introduction to Mohr's circle, and we just chose one. And so how does this relate to the Mohr's circle? Well, we took a element and we said, hey, we got this going on. Some sort of sigma, and it's proportional to the tension. Like obviously a free body diagram is just, hey, we got two tensions, on some, but you can take the bar and say, hey, we have tension, and then what we do is we take a small element, and theoretically this becomes infinitesimally small. And again, the reason you do that, because if we have a beam and a lot is going on, things are going to vary. Like at any one point, you're going to have a different axial tension. You're going to have different shear forces. The shear force here, if I take a cut, is going to be different than there. And so, but as this little square gets to be the size of a point, and very infinitesimally small, even a point that big has got plenty of molecules to deal with. It's got more. I was thinking like you could break this down to at least 8 molecules. Your cube could be 8 molecules, and there's more than 8 molecules if in that piece of ink right there. So hella more than 8 molecules. Anyway, so yeah, so infinitesimally small, and what happens is that the pressures are going to be the same on both sides. If we take a cut, the forces would be the same on both sides, whether we take the cut that way. And yeah, and so and the pressures are going to be I was just going to say the same, but yeah, we deal in pressures because it doesn't matter if I have a 1-inch bar or a 1/4 inch, or just like a 1/2-inch bar. If I have a bar of steel that's 1/2 by 1/2, the area is 1/4, and this can only take 58,000 pounds divided by 4. It can take a tension of 58,000 pounds divided by 4. But the pressure will be this. It'll be that force divided by the area. So it's going to be 58,000 divided by 4 divided by 4. And did I mess up this algebraic thing? It's 58,000. No, that's fine. So why am I messing up here? The pressure, no, the pressure is 58,000. Okay, so if, let's see, let's go back to pressure is in force per length squared. So the force is going to be 58,000 divided by 4, and the area is going to be not 4, the area is going to be 1/4. Holy hell. Yep, so you got 1/4 the area down there. Now you can take this and invert it and bring up a 4, force cancel, and you get the same pressure. You get a pressure of 58,000. And so so that's why we deal in pressures. And then, again, that's the take-home point for mechanics of materials is like, if that pressure gets to be big enough, if that pressure exceeds the max pressure, 58,000 or 29,000, or whatever the material can handle in shear, tension, compression. If it's wood, these 3 numbers are going to be different numbers. But if one of those numbers is bigger, then we got issues, and we need to like resize our whatever we're building. Oh, cool. So here's how it relates to Mohr's circle. So we just came up with a bar that we're just tensioning, and it didn't look like it had any shear at all. You know what I mean? I don't see a shear arrow. But if we rotate that at a 45, just because we took our cut at a 45, hell yeah, it's going to shear at a 45. And and then that did come into play. So just like the idea of tensioning a bar, you're just like, okay, it can take that much. And the fact that it's going to fail in shear just because it's going to, at a 45 degree angle. And so that's why if you have any material, you have to pretend that it's, you know what I mean? Let's say you just had a material that was made of double-sided tape. You know what I mean? It's just double-sided tape. So, and that's the strength of it. So it wouldn't matter if you took a block of double-sided tape like this, and then put a strip of double-sided tape right there. It would, it would be like the thing was just made purely out of double-sided tape. So that's a good analogy for how things are, you know what I mean, the strength of things. Now, in our bar analogy, when we're tensioning it, 45 is just the perfect place where we get 70%, the shear is 70% of this tension, because if our cut is steeper, well then this normal force, you know what I mean, to get to the parallelogram method, to get to this arrow, I'm going to go, hella shallow and then just very steep. So the shear force, almost approaches 0, even though the area is 1 inch. You know what I mean? My shear stress is almost 0. It's very low. And then the opposite is, well, what if this is our bar, and what if we take a longer cut? So I have this tension, and that tension arrow is that long. I have this longer cut. And so now this normal force is going to be fairly steep. And so what that's going to be, what's going to happen is, so if here is the length of this arrow, this tension arrow, this is what I need to do. And I need to follow this parallelogram method. Says, hey, you follow this parallel. And so, hey, this is the shear now. So this is the shear, and then we have very little normal force. You know what I mean? What you would consider in tension. And then, but our shear force is not huge, though. You know what I mean? So our shear force could approach 58,000. But look, if I'm saying this is an area of 1 square inch, look at this area. I mean, just how many squares could I put in just visually right here? 1, 2, 3, 4, 1, 2, 3, 4, 5. So cool, I'm basically taking this divided by 5. You know what I mean? 60 divided by 6 is 10. I don't know. So it's like, anyway, so yeah. So your pressure is now 58,000 divided by 5 square inches. Let's say it's 5.8 square inches, and so your pressure is going to be 10,000 pounds, which is way less than 29,000, which would rip this apart in shear. So that's and this really brings the idea of sines and cosines and circles, because you know what I mean, and maximization, because we just showed that, hey, if I vary this angle, from totally steep, I don't have any shear. You know what I mean? If I just make that cut, it's going to fail in tension, along that cut. We said if these were, molecules that are getting ripped apart that way, and if we have a slight angle, hey, there's hardly any shear, and if our angle is really big, as big as it could be for this scenario, it's pretty small anyway. And so it goes from 0 to, and as we rotate this to a 45, it gets to be a max. It gets to be 29,000. And then as we steepen that, as we go from 45 to 60 to 75 to 85, and we make this this angle, or how would you say that? And what we say is that the face of this cut is the angle from the horizontal. And so if we make that cut at a 45, this is our face, and this is an angle of 45 from the horizontal. And so if we steepen that cut like this, then this angle steepens to maybe like 60 degrees. So, cool. And as we steepen that angle, we just said the shear force reduces. So from 0, the shear force is 0. At 45, we get max. And then at like 60 degrees, we go back down to 10,000. So if we had an equation, we would go increasing to our max and then decreasing. And you could theoretically take the angle to where, your cut is like this, and you're not going to have any shear forces. And the reason you're not at this, it seems like, well, what if I pull on this top part and then pull on this bottom part? Yeah, but you're not. The stress says that you're having equal tension. So if I had arrows here, I would have an arrow right there and an arrow right there, an arrow, and that also brings up the definition. Shear is if two things are sliding across each other. If you have something like this, and let's say you have two pieces of wood, or what's stretchy that we can visualize? Hell yeah. So I think have a strip of double-sided tape. So if you had a strip of double-sided tape and we had it on a material that you could visibly stretch out. Like double-sided tape is stretchy, right? But the whole idea is like what we don't want is those two things to rip the tape sideways. That would be shear. But if I'm just saying I'm pulling here and here and I'm lengthening this, that's fine. I can lengthen this thing. The double-sided tape will lengthen, but it's not going to rip apart. Like it'll have no shear. The double-sided tape might lengthen and then tear. Cool. You know what I mean? And maybe this is two rubber bands with a layer of double-sided tape in between the rubber bands. And so yes, in that case, if you actually got the double-sided tape to perfectly stick to the rubber bands without shearing across the rubber bands, because as you pull on it, the rubber bands actually, yeah, that's kind of cool, because the Poisson's ratio, the rubber bands want to, yeah, so you do get shear stresses because, that's fast, but yeah, make it simple is, let's say the double-sided tape can stretch and the rubber bands can stretch. What were we saying? Oh yeah, that would just be a place where, hey, the double-sided tape probably can't stretch too much, and so the double-sided tape's going to break where the rubber bands are still attached to the double-sided tape. So that would be double-sided tape fails in a normal force, but at no point did anything fail in shear. Anyway, so cool. So we just showed that we can vary that angle, and 45 seemed to be a max. But 45 was just a max for this perfect thing of taking a steel bar and tensioning it on both sides. If we add some compressive forces in either direction, that's going to change things around. It's not going to be things are going to be a little bit different. And so when we do make our angled cuts, hey, yeah, we're going to get a shear force, and we're going to get a normal force, and maybe this normal force gets bigger. You know what I mean? Because if we start with something where we have, sigma x, sigma y, and then a shear tau xy, as we rotate this and we make our cuts and do those free body diagrams, maybe one of these gets real big, the other gets real small, and maybe this one goes away to 0, and so that's more circle. And if we're just saying, like, the worst case scenario would be like, hey, these numbers are all just average, but then when we rotate them, one gets huge, and then it would be a bigger number that the material can handle. And so, that's kind of the fascinating thing with tension. It doesn't look like there's any shear, but as we rotate it, we induce this shear concept, and that number might get big, and we might have to, you know what I mean, and that might fail the system. And just the fact that we didn't start with an element that had shear is you might overlook that. Okay, hell yeah. So that's going to be the introduction for Mohr's circle. And now I'm going to try and make a video on doing the diagram of Mohr's circle. And at least we can end with what the diagram would be. You're going to have an axis, and you can put the axes anywhere, but you have to have a center. And for sign convention purposes, you're in this x direction. This is going to be stress x sigma x1. And what we're gonna, if we have our element, we're gonna call this sigma x, sigma y, tau xy. If we rotated this element, we said from the horizontal we rotated up, this face is now going to be at a different angle. So we're going to rotate this element. This face is now at a different angle from the horizontal. And we're going to say this is the x1 direction, this is the y1 direction. And this is the angle that we rotated. Cool. So on our diagram, now on our diagram, this is not the x1 direction. This is when we rotate this, we're going to get a stress on that face that's sigma x1. And we're going to get a stress over here, sigma y1. And we're going to get a shear, tau x1, y1. And when we do this, we're only interested in we're only interested in the shear stress on this face that we rotated. I think that's a good way to look at it. And when we do rotate it, we'll get this shear stress, we'll get this normal stress, sorry. We're only interested in the normal stress on this face. And when we compare to the normal stress, we're not interested in the normal stress on that face, not really. And when we do rotate this, we'll be able to get the normal stress on this face and the shear stress. And to get this value, we would just rotate the angle another 90 degrees. From here, plus 90 degrees. And then this would be synonymous with sigma x1. You know what I mean? So that's kind of the equation that we're using. So that way, you only have to use one equation. You know what I mean? Because if I'm going to rotate this up an angle, I can get this value. And I just know that I got to rotate 90 degrees more to get that value. Hell yeah. So on Mohr's circle, we have tau x1, y1. And if we have our little element that has a sigma x, a sigma y, and a tau xy, these are still values that we will hit on here. And alright, this will be good because if I end the video like this, I'll be more solid if I make this. And maybe, you know, I just went over this. But hey, let's say this is just a positive. Let's say these are just all positive numbers. Cool. So I'm going to put, and we're going to say sigma x is just a little bit bigger. Cool. So I'm going to go, and then this is the normal stress. So this is 0. This is 0 normal stress, 0 shear stress. That's the our diagram. So if I'm going to plot this one, I'm going to go, hey, sigma, this is going to be maybe over here, and then this is less. So let's say it's just right there. Cool. And if we have all right, hell yeah. So I'm totally new to this. So let's say we didn't have any shear stress. We just have these two normal stresses, and we need to make a circle, right? So this is the center of the circle will always be between sigma x and sigma y. So we're going to put our center of the circle there, and these aren't associated. And so yeah, we'll get to where we actually include that. But here's going to be our circle. And so for this one, because this is sigma x and this is sigma y, here is the angle 0. And because of the equations are like a 2 theta, if I wanted to get up to this point right here, or this point right here, so this is, and when it comes to shear, it doesn't matter, like your shear is going to, doesn't matter if it's negative shear or positive shear. Like that's the location of max shear, and we see that. And the location of max shear is when sigma x and sigma y are the same. So why I got confused just a second ago is because I'm new to this, and so I didn't realize that these are actually points. You know, they have 2 coordinate points. So if I say this is sigma x, this sigma x is sigma x tau tau x y is equal to 0. And if this is sigma y, this is tau xy is equal to 0. Ooh, and I can explain this now. Okay, hell yeah. Because and so so this value up here is going to be, you know, half the distance. So this value right here is going to be sigma x plus sigma y divided by 2. This equation, I probably graduated without knowing how to find the midpoint of between 2 different things. You know what I mean? You actually add them together and then divide by 2. You know what I mean? It's kind of fascinating. Hell yeah. So so that's going to be that midpoint, and then our coordinate will be tau x1, y1, kind of a negative. And that will be the maximum that gets. And because this is our, and this line right here, and we'll set up another one to show you. This line is associated with an angle of 0. You know what I mean? Just like here, this our element is rotated an angle of 0 degrees. Now, it looks like this point is at 90 degrees, but there's a 2 theta involved. So if I say this is 90 degrees, you know, on this diagram, that's going to be 90 is equal to 2 theta, and we're going to divide by 2. And so the actual angle is going to be 90 divided, it's going to be 45. So then an angle on here, visually, you're going to half it, and so you're going to say the shear is going to be maximum at 45. Let's do that biaxial stress just so we can crush some of these out. Sigma x1, tau x1, y1. Because that's what I wanted to do. I just wanted to play around with this. And so if we have sigma x, and then no sigma y, and then no shear. So our sigma x is going to be a pretty decent value. So that's going to be like right there. Sigma y is going to be 0. I can still plot that point. And you know, back when I was confused, these are still, this sigma x is associated also with this tau xy. And that's what I didn't realize a few moments ago. And so when we actually include this tau xy, we're going to show how this sigma y is related to this, because if we're saying this is the positive tau xy, sorry, I'm drawing it positive, we're going to say that sigma y is associated with this shear. And we're going to see, let's just talk about that right now since we're doing it. If this sigma x is associated with this positive tau xy, and then on this face we said that, hey, if this is positive this way, forces in the y have to be balanced, and then this is going to cause a rotation, and then so we have to have a counteracting rotation, and then so this is going to be associated with positive shear. How we start with 1, we say, hey, this is x, this is y, we have a shear on the positive x face and the positive y direction. And once we know 1, we know all 4. And that's the way I would do it. Some people just say, hey, these arrows touch, and then these arrows go away from each other. I don't know. I would just say, hey, this has to be balanced by that. This causes a rotation, and this counteracts that rotation, and then everything's equal. And what we said was that if we wanted to find the elements on this face, we treat it like the sigma x1. Even when we rotate this face up a little bit, we still say this is sigma x1. It's rotated the angle theta. And so we do the same thing for sigma y. We just say it's rotated an extra 90. And then now I'm kind of cooking, because on here we said if we wrote an angle on here of 90, we have to double. That's going to be a 180. Cool. So now let's show. And then what happens with the shear, though? And so this is very fascinating, because if I say this, I almost need to draw it again, and that's fine. If I say, yeah, so let's get these arrows. Positive shear. We have a sigma x. Same on that side, sigma x. And then we have a sigma y. And then a sigma y. But let's say I do rotate this element to 90 degrees. This becomes my x1 axis, and this is synonymous with sigma x1. And if this is my x1 axis, so this was the original xy axis, and if I rotate this, I always take this. This is kind of a new one to me this year. It's like, hey, let's take this, and if I rotate this axis, this is going to be x, this is going to be y, and when I rotate it, it then becomes x1, y1. And we're going to rotate this 90 degrees. Cool. When we do that, hell yeah, this is the x1 axis, but look at this. This now becomes the y1 axis, and look at this shear. This shear is on a positive face in the negative direction. So if I'm calling this shear tau x1, y1, it's actually negative. It's in a positive face, but it's in the negative y1 direction. So that's why on our plot, so now we can kind of go back to our diagram and see where we're at. I think we should now just go for it and plot something that has a sigma x, a sigma y, and a positive shear tau xy. And let's say this is big, let's say this is medium, and this is just a normal number. So now we can come to our graph. This is going to be sigma x1. This is going to be tau x1, y1. Now they do this down here just for whatever reason. I can't explain it, but that they throw this one down here for reasons. Mainly, I mean, probably the asterisks are going on the page right now. It is related to probably what we're talking about. Anyway. But it has to be more of a visual thing, because it wouldn't matter if this is just up there. So there must be something visual. Oh yeah, all this is like, hey, if we want the angle to rotate this direction, we want this tau x1 y1 to be down here. And let's see why that. Anyway, so let's throw these in. So so this sigma x1. Oh, and that's fascinating, because even this circle, even this initial condition, oh, that's so fascinating. This is theta is equal to 0. Like you could say, hey, I have an element that's already rotated, and I have this, and this, and these are numbers. You know what I mean? And let's say I want to unrotate it. Well, then I have to, like, you know, if I have to unrotate it 25 degrees, you know, it'd be like rotating it 360. Oof, I hate simple math. 335. I would have to rotate this 335 degrees. So if somebody gave me an element that was already rotated 25 with, like, you know, the shear and then the normals, and I wanted, and that's just my initial, I mean, you could say that. There's no reason you can't just say, hey, sigma x, sigma y, and then tau, and we're just saying this element is theta is equal to 25, and that's our starting position. And I want to rotate it 335 degrees, because that's would be synonymous with just an element in its zero rotated state. Alright, that was probably too much, but same thing here. If we have an element, in a zero rotated state, you can still say it's rotated 0 degrees. And I think that's useful. So now this axis becomes x1. So this axis is x, and it's also x1. This axis, and then keep in mind, because this axis for theta is equal to 0, if we want to plot this point on this thing, we have to say, we have to actually make this sigma x1 axis up here, and then this is sigma y1. So we have two different things going on. If I want to plot these 2 points, I say, hey, sigma x1 is this larger number, and then it's but it's not just right there. This is the point. These two are on this face. So now I'm kind of getting it. Is that you have at the angle 0, you have these two are points on this graph. So we're going to go over sigma x1, this number, and then in the positive direction, we're going to go down this far. Cool, so let's just do that. Hell yeah. And then to plot this point, I have to treat it like I rotated it 90. And then what I'm going to do is then say, cool, sigma x1 is this value, and it's just a little bit less, or it's that much less. And it's associated with the shear on that face as well. So, and sorry I didn't draw these in. If this is positive, this is that direction. So these 4 are associated with positive shear. We already said that. You start with this one, positive face in the positive direction, and then find all the other ones. But when we go to plot this point, my y-axis changed. So this shear is now on a positive x face, but it's in the negative y direction. So then when we plot this point, and then sigma y becomes sigma x1. So we're rotating this to be 90, and I want to plot this and then the associated shear. So so this value becomes sigma x1, and it's on. This is the graph of sigma x1, tau x1, y1, and so I can plot that value. So this is synonymous with sigma y, sure. This is synonymous with sigma x in that direction, and this is synonymous with, in this direction, tau xy. But here, because this is going to be a negative, this still has the same magnitude of tau xy, but it's going to be in the negative direction. Positive face, negative. All right, hell yeah. So now we're on a roll, because I think that's probably the hardest thing about the MOHR'S circle, and even just the transformation equations in general, where you're just like, ooh, this sigma y, it's got a y in it. Why would I ever associate that with sigma x1? Well, to plot that value, or to analyze that value, it's the same thing as rotating it up to that angle. And so, and then down the line, if I am rotating this element, let's say 10 degrees, then sigma y is going to be that it'd be synonymous with that element being rotated 90 plus 10, or 100 degrees. All right, so hell yeah. So let's plot this point. We spent a lot of time talking about how this shear is going to be negative, but it's still equal to this tau x1. So we're going to plot sigma y, and then the negative, equal that distance. And then hell yeah. And now what we have is we have enough points for our circle. One of the aspects of the MOHR'S circle is that, and we'll see this in a second, is that the halfway point between any sigma x and sigma y terms. It doesn't matter what they are. We can find them all. But the halfway point is always going to be the center of the circle. And then Should I break out a compass? Hell yeah, I made this video. This is pretty sweet. 3 zip ties and just taking the inner guts of this pen, because, yeah, a compass should always be just a pen. And slide it into place. Booyah. So we're just going to, let's see if this works first go. Better. Yeah, there we go. Juice the pen up. Alright, so we're going to go through both those points. Try to. Alright, hell yeah. So there's our circle. We can even get a ruler. And what we're going to, and let's go back to these original points. So this point is sigma x, tau xy. This point up here is sigma y, negative tau xy. And we understand why it's a negative. Cool. And then furthermore, circle, I mean, this part's probably the heady part, is that this line right here is associated with theta is equal to 0. That's probably going to melt your mind, be like, well, why isn't Mohr's circle always just this is going to be theta equals 0? Well, that's kind of the benefit, or that's just what happens with the equations come out in the wash like this. But this is your starting position. And so you can see that this starting position is not maxed out. For this starting position, we had a big value of tension, we had a smaller value of tension, and we had some positive shear. And we can see that, hey, this graph says that we can get a substantially larger value for our normal stress. Now in this direction, you can't say this is substantially larger. Well, it's smaller. Like this is going towards compression. This is going to be going towards max tension in stress. But this is actually approaching a 0 value. Like nothing's going on that face. So, and this circle can be dead center, where one part is going to be in max tension and the other part's going to be in max compression. So the aspects of this circle are that it can't, because the shear stresses are all the same, this circle can't migrate this way. You know what I mean? So we do have the equation of a circle, but at least it can't move this way. This circle can hella move any way this way. We can have like everything is in compression. We can have, in this case, everything is always going to be in tension. And then your shear forces are going to be between positive and negative. And I can even explain that positive and negative right now, because you're just like, well, explain that. You know what I mean? Why would that be? We took this bar and we made an angle like that, and we were just happy as a clam. And we can also do a steeper angle. This will really show it. If we do tension, shear is two surfaces moving across each other. So in both these cases, you're going to have like movement this way. So we're going to have, and I don't even know if this is actually going to work out. And so I was just going to draw this picture where you have the angle is like 45 degrees the other way. So, you know what I mean? So yeah. So so if this is our two biscuits, and we're pulling this way on them, that's not this picture. Sorry about that. That's this picture. Yeah, I'm glad I'm doing this because this gets me up to speed. So this picture is, hey, something on top is getting pulled across something on the bottom. And what happens when we have this is that we're going to say, what's going to happen here if we have a square element on here? or it's better to be like, hey, this is synonymous with this. If I take this little block, what's going to happen to this? It's going to look like the top surface. And yeah, I think it's good to get used to drawing little boxes, what happens to them in shear. So if I do have this box, and I say the top surface is going to be that way now, and then the bottom surface is going to be that way. That's kind of what I do. Those are the first two things. And you could just say satisfied. Let's just draw that angle. And I think it is useful to draw pure shear. So we're going to do those two dots, these two dots, and what we want, because these are associated with two forces this way, but they have to be balanced. That would just cause rotation. So the only way to actually slide two things across each other, you think it's just these two forces, but literally, I've done this with a balloon. Sorry, the balloon is inflated. I don't even know where it is. I got a lot of papers going on. But it would be the same thing as taking a circle and being like, I'm going to put an upward force and a downward force. Well, you're just going to turn it in a circle. So if this is that, you know what I mean? Hey, it's just going to turn in a circle. The only way to pull something apart from each other, so we have these two forces separated by a distance, and they're causing a couple that way. We have to have two forces this way and that way. So on our diagram, you know what I mean? So, hey, anytime that you can actually draw these four shear forces or shear stresses in, I definitely would. Because then this is a good tip, is like, how do you get from there to actually drawing this shape? Because when you do have shear, these lengths don't change. Because if I drew this, it looks like, hey, that got longer, this didn't change. But if we have shear, these lengths do not change length. Okay, so to draw these dots, I'm going to, so those go that way, these go that way. And well, actually, let's slow down because we need some sort of method. I always start, like, you know, set this as my coordinate axes, and this will help us determine whether it's going to be positive shear or negative shear. And the way we have this drawn, actually, this is going to be a positive x face, this is positive y, so this is going to be negative shear. So let's see what shape is associated with negative shear. This is the harder one to draw. And so let's draw the easier one first. So we're going to draw positive shear, positive x face, positive y direction. This sets up this one. This sets up the rotation, this is counter rotation, and we have positive shear. Now what this element is going to look like, so this is kind of what it looked like. I'm going to start from this point. I'm going to fix this point, and then I'm going to go to this surface and say, hey, this surface moved up that much. So I'm going to bring the bottom up and the top up the same amount. Now this line, surface, moved this direction, kind of equal amount. And but these 2 points have to match, so I'm just going to kind of box it in, you know what I mean, and then put it right there. And then so I have this shape is associated with positive shear. And so let's see if you can see that on this. You know what I mean? We're going to have some sort of element and it's going to resemble this. You know what I mean? If we do have maybe not these angles. I bet you something is up with, you know, the angles and then this little box. But if we have shear, you know, associated with the top getting pulled this way and a bottom getting pulled out from underneath it, and we have this box, hell yeah, is that we're going to have the top surface go this way, bottom surface go that way. This thing ain't rotating, and so this is causing a couple. We need to balance that couple with a downward and an upward. And what the hell? Why did we, oh, we drew the same picture twice. And so, yeah, no, this, yeah, so this was supposed to be the one down here. This is the positive shear one. This is a force this direction and a force this direction. This is causing a rotation this way. We have to balance this with an upward and a downward force. And this one is going to be associated with positive shear. So this face goes up, this face goes over. If I make this pivot point right here, the diamond shape will look like that. And if this is my coordinate system, the diamond shape will all be in that first quadrant, second quadrant, third quadrant, fourth quadrant. Now, negative shear, it's going to get fatter. It's going to be a diamond shape, but it's going to spill into those two quadrants. So that's what we're going to look at now. So we had, this was negative shear. Positive X face, negative Y direction, and then equal and opposite, causing a rotation, and then so we have to counteract that. All right, so let's draw what the element, kind of dot in what the element looks like, pivot it there, and then I'm going to go to these two faces. This face is going to go down. This face is going to go over. I know that these two have to be the same point, and so, you know, box it in, and that's going to be that point. So as this goes over, like, you know, the negative one's a little bit harder to see because you're like, ooh, it was easier, definitely easier to see. You know, as this went up and this went up, hell yeah, those kind of have to meet right there. Well, as this one goes down and this one goes over, they have to meet right there. So this shape is the diamond shape that you get. And I've seen professors even just like, they don't have a rhyme or reason to draw this. And so that's why I spent, developed my own rhyme and reason to make sure I could draw this shape every time. Because you want to make sure that these lengths don't change. And you want, and the shape is a little bit odd. And so here's our original axes, and this was first quadrant, second quadrant, third quadrant, fourth quadrant. And you can see it spills out into the second and fourth quadrant. It gets squat this way, it's a diamond shape, but this is going to be negative shear. And this was associated with positive shear. And all it takes is to find one shear force. And I got to get better. If I watch the video right now, I just said shear force, which is not, I mean, I guess, yeah. Shear stress is synonymous with shear force. But yeah, it's good to be heads up and be like, what are you saying? Because we're talking about shear stresses. Obviously, this is an element, you know what I mean? It's a three-dimensional cube. And so the pressures, the shear pressures are a force on that area, you know what I mean? So, I mean, the pressures and that area combine to make a force. But again, the idea of material mechanics is we have numbers for those pressures. Those pressures can only get so big for those three terms: tension, compression, and shear. And so, all right, so back to Mohr's circle. Oh yeah, so that, why we did that is we showed that if we have an angle, and again, this is the face that we cut, it's 45 degrees from the horizontal. This face would be, like this face right here, would be 90 degrees plus 45. So you can see that this face is 135 degrees from the horizontal. It's 45 plus that 90 component. And what happens on this face is that we have a sign change for our shear. That was the whole reason to do that. And sorry we went, well, no, I think we did good because we actually talked about how to draw those things. Always take your shape and lock it in on that, you know, kind of like reading a book. Or, I mean, not like, we'll just, you know, like a XY coordinate system, you know, lock in the origin and then see what these two faces are doing. This one's going up, this one's going over, same amount. Meet in the middle, and then hell yeah, and then it's all in the first quadrant. This is positive. The diamond shape looks like a diamond that way. The other one looks like a squat, object, but still a diamond. All right, booyah. Oh, got a little messy. All right, so cool. So I think we were talking about why, you have negative shear. Maybe why your Y face is negative. I don't even know why we did that. But yes, that's why at 90 degrees, if you have a value and you go 90 degrees from it, your shear force changes sign. And back to this is a 2 theta representation. So if I go from here all the way around to there 180 degrees, that's like rotating 90 degrees on our object. And so here we said was theta is equal to 0. And then so here is theta is equal to 90. That's probably going to be a very hard counterintuitive thing to look at, but something to get used to. So, because we already plotted sigma x and we plotted sigma y, we just didn't know why we had a sign change. And so we just tried to explain that, and we did a pretty good job. And it's because our x1 axis is right there with the y1 axis shifted that direction. You know what I mean? So this now is in a negative direction, and we want to account for that. Okay, sweet. And so this diagram shows that, hey, our max shear is going to be more. And yep. And the other thing that happens on this, from this first one, if we didn't have any shear force, if this was shear stress, if we didn't have any shear stress, but we did have a sigma x and a sigma y, these points are just right on. They don't, it's sigma x, but with 0 shear. So it's that point and that point. Let's see. What was I getting at? Alright, hell yeah. I realize where I want to go with this. So the whole reason I wanted to make this video is from the who cares perspective. It's just you're given 2 initial points, or 3 initial points. You just want to know what the maxes are, and you want to know if you're going to be surprised or not. And so in this case, your shear stress is just a little bit bigger. This isn't the max shear, but you're just a little bit. So you're not going to be too surprised about that given this diagram. And even your max normal stress, it gets bigger, but not a massive amount. And so what orientation on here might you be shocked at? I think when your shear stress is maxed, so if you're given an initial sigma x and sigma y right here, if this is going to be your sigma x with that positive shear down here, and this is going to be your initial theta is equal to 0. And so, yeah, and so that comes from the scenario where sigma x, let's just throw a value on it, is 4,000. Sigma y is 4,000. And these are the same. So if you see that these are the same, and you're given a shear force, so us, let's just say that's going to be also 4,000, then here is your initial condition. This is a rotated element at 0 degrees, 0 degrees rotation, and sigma x is equal to sigma y. So we have a point that's 4,000, 4,000 right there. We got a point that's 4,000, negative 4,000 right there. And so if that's our circle, it would actually have to go through the origin right there. So hell yeah. So if you're given a problem where tension and your tension on the y is the same as your tension on the x, tension x is the same as tension on the y, and you have a shear, then what are we going to be surprised at? Your shear is just maxed out. So that's useful. If I ever see a problem where the sigma x and sigma y are the same, whatever the shear force is max. It could be 0. We'll talk about that in a second, and we'll talk about that right now, because that's probably the elephant in the room. Is just what? Well, let's say your sigma x is right here. So this is sigma x, and shear is 0. Cool. And then you got sigma y. And so that's going to be a rotated element at 90, but your sigma y is right there, sigma y, and then your shear is going to be negative 0. Okay, it's still the same point. And guess what? Your Mohr's circle is just that point. You know what I mean? So rotate all day long, you're never going to pick up a shear stress. Sigma x1, y1 is 0 all day long. And that's going to be the case where you have tension on both sides. And, you know what I mean? That's the coolness about this is like, hey, let's throw in compression. So if I set that up, this is sigma x1, this is tau x1, y1. I'm going to say both these are negative 4,000 in compression in the x and y. And so that's going to be a point over here. This is going to be sigma x is 4,000. And then with a shear of 0. So this point is going to be, negative, so this is going to be negative 4,000, 0. That's sigma x. Sigma y is going to be negative 4,000, and it's going to be negative 0. Because you got sigma y, and then you have negative that shear, that initial shear, shear tau xy. So if we say tau xy is 0, you know what I mean, then we have this point that's negative 4,000, negative 0. And I just do this just to like re-emphasize why that's a negative. We already talked about that. It's you're bringing the x1 axis to here, which means your y1 axis is here. And you know, you had if this was 0 positive shear in the positive 0 direction, well, hey, it's now related to this new y1 axis. It's positive face, negative direction. You know, so even though you're thinking of it as a 0 component, you can still try to make it have a sign. All right, so hell yeah. So then you have this point out here, and then so there's your circle right there. Because you have 2 points, they're overlapping each other. You take the middle of those, and that's going to be the center of your circle, and the circle goes through all 3 points. So that's the take-home point for Mohr's circle: x1, tau x1, y1. Find the point for x tau. So it could be there. Find the point for sigma 1. Sigma y. And that's going to be negative this same distance. So the only thing that has to, if you plotted your initial x right there, the only thing that has to jive is that your the shear has to be the same, equal and opposite. And then so wherever sigma y, it doesn't really matter. It could be right here, and you could have a circle right there. We could have sigma y as hella negative. You know what I mean? And then, you know what I mean? Then this is our origin. Sigma y is right there, sigma x is right there, the shear is the same, and this circle has to go through these points. So sigma y, sigma x, we're going to say the center of the circle, and then here's our coordinate axes. The center of the circle has to be at the midpoint between sigma x and sigma y, and so we're going to say that's our center point. And then the circle goes through those points. And we'll see what we're surprised with from this scenario. So if I was given this as my sigma x, tau x, y, and then here's this point, sigma y, tau, negative tau x, y, as my, and this is going to be, you know, the angle 0. So what would I be impressed with? The fact that because the shear stress was pretty small, and these values were, the difference between these values was pretty big. Yeah, because we just talked about how if sigma x is equal to sigma y, the shear stress is going to be max. Whatever this shear stress is, whether it's a number, whether it's 0, whether it's negative or positive, this becomes the max. And so if I have a sigma x that's a huge positive number, and then a sigma y that's a, even just a normal negative number, we have a significant difference between these. And so if I have a tau xy, that's, yeah, and it doesn't even matter, you know what I mean? The greater this is, it doesn't even it out. Still, like whatever this number is, it's going to get bigger, like substantially bigger, because because here I just said the initial shear was kind of small, and so we can do one where the initial shear is pretty big. And let's say still the difference between tau x and tau y is big. The center of the circle is going to be there. And we're going to say here's the point for that one, and then here's the point for that one. And we're going to graph this circle, and we're going to see what's surprising. What's surprising is like, hey, look at that. The shear is going to be big. You know what I mean? The shear is going to be big down there. So even though our initial shear was big, the fact that sigma x was a pretty substantial number to begin with, and sigma y was negative, so there was a huge difference between sigma x and sigma y, that even though we had this initial shear that was pretty big, well, guess what? We get extra big shear. So now I can intuit, at least, that was the whole idea, is like sit down and go through these. So like when I see a problem, I can be like, ooh, there's a huge difference. Sigma x is a big positive, sigma y is a big negative, and that's a big difference. Or sigma x is a big number in the positive, and sigma y is 0. Still a big difference, you know what I mean? Sigma x is negative, big number. Sigma y is 0. Sigma x is 0, and then just reverse. Sigma y is a big negative number, big positive, big negative. There's a big difference between these. And sigma x is big negative. Sigma y is a big positive. Big difference. And then, so whatever the shear could be 0, it could be a small number, it could be a big number. But what this will indicate is that we will be increasing the shear on a plane, or when we do the if this is a big difference, doesn't matter what our initial shear is at theta is equal to 0 with an unrotated element, we're going to find an angle that we're going to get a quite large value for the shear. Then I'm going to try to answer one of the questions that's going through my head right now. We had a sigma x with a pretty substantial shear initially, but what if we had sigma x with no shear and sigma y with no shear? Well, hey, like look at this. Our actual circle doesn't really change too much, so that's kind of interesting. You know what I mean? So you can have a pretty decent initial shear, on your unrotated element, but the driving factor of this max shear is just the difference between these. That's what's driving this number. And so and what would be a placement that, yeah, I mean, well, yeah, if this is double, let's try that. So if this is actually double this, and this is double, well, no, that makes it substantial. Yeah, I would say that, I don't know. And does that actually proportionally double the shear? Like if I had this as 0 initial shear on the 0 rotated face, I don't know. Look at this. No, because I actually give it quite a bit, and we don't get too much extra max shear. Anyway, all right. So hell yeah. I mean, circles. I don't know. You kind of got to play around with them. All right. So I think that about covers it. So we have this axis, sigma x1, tau x1, y1, we're going to plot a sigma x and a sigma y. It doesn't have to be that way. Sigma x could be a negative. Sigma y could be a positive right there. Halfway point's the center of the circle. But sigma x is associated with the initial element could be associated with a positive or negative shear. Let's just do a negative shear, and we got a negative sigma, and let's do a positive sigma y. So we're going to have negative sigma with a negative shear, just go down to there, and then a positive, we'll just do positive. So this is sigma y, and then we're going to, this shear becomes a negative value, is the same as that. And then the halfway point is going to be our center of the circle. And we're going to, graph it out. And so, booyah, booyah. All right, so those are our points. What's going to happen is that sigma y is going to get bigger. Oh, and we should talk about this. So now we need to talk about the angles. So this was our sigma x, this was our sigma y. This is associated with 0 degrees. So if I say that this sweeping out this much, if I take my initial element and I change its angle, and if we rotate it this way, we're saying that's why we put this down here, because we have a positive rotation. Then I'm going to rotate it out this far. And so let's just kind of guess what this is. This looks like, let's say this is just 40 and 90. So that's going to be 130. And so if this angle is 130, I actually only rotate the element half this. That's going to be 15 plus 50, 65. So then I know my max. And so check this out. This is my coordinate system. And this is sigma x1. And it's going to be a positive. It's not the max, though. Look at this. This is a max in the fact that it's a big negative. Like this is more negative than this is positive, because here's my axes. So I would say this is associated with the sigma 2. It's the second principle. It's not the max. Sigma 1 is the max, and that would be right here. And so honestly, if I rotated this element 65 degrees, I'm getting a principal axis. But I'm not getting the max. The max on that. And now we got this. Yeah, this is cool, because this shows that if we take our element and then rotate it about 65 degrees, and we started our element with a big negative and then a smaller positive. So small positive, big negative, and then what did we have for shear? We had a negative shear that was kind of substantial. And if we rotate at 65, this face becomes a positive number, but it's not that big. But on this face, we get a big negative. So this is a positive number in tension, but we get a big negative number on this face to happen. So rotating 65, this is a principle. It's principle because there's no stress. See, at this point there's just no shear stress. So that just becomes 0, and that's the place where these are going to be. One of them is going to be max. It has to be. Because we have an origin, and one's either going to be a negative max or one's going to be a positive max, depending on where our circle is shifted. And cool. So we rotated it up 65. That gives us, this becomes the sigma x1 If we do rotate 65 degrees, this becomes sigma x1. This becomes our y1 axis. So this is x1 axis, y1 axis. If I notice that this number is the biggest, well, I got to rotate to it. So I got to rotate another 90. So we're going to go 90 plus 65 is 155. And then I got to double this. That's going to be 310 degrees. And then so, well, two different things. Because so 155 is going to be the angle, and we're going to say this is going to be the max principal. So it's principal angle number 1. If I rotate this initial angle 155 degrees, this becomes my x1 axis, and sigma x1 right here is maxed. And then sigma y1 becomes right here. You know what I mean? And so, yep, and that angle is 155. On the Mohr's circle, because everything is a 2 theta, I can see that if this is my initial angle, I always have to go in this direction. And that's because we put this, we make this graph, that's the reason we put this down here. The positive is down here. That means that a positive, when I travel this way around the circle, it just makes the sines and cosines, part of those transformation equations, work. So I'm going to rotate. So if this was 40 degrees right here, this is 50. And so I'm going to have 360 minus 50. That's 310. I'm going to rotate 310 degrees to get to this max number. And hell yeah. But 310 degrees, I'm going to rotate 310 degrees. 310 degrees to get to that max number is a rotated element of just half this. So it's going to be 155. So if I rotate my element, you know what I mean, this is 90... no, this is 180. 30 degrees would be 150. So there you go. I'm going to rotate this element. I'm going to take this face and then make it faced that direction. So that's going to be my element. I started with this face, and then now that became that face. So this face rotated 155 degrees. Cool. Sigma x1. And then this becomes sigma y1. Second principal stress, the lower one, and this is the first principal, the max. Both of these are principal stresses. This one's just the max. Hell yeah. All right, so I'm glad I was about to not go over like the angles involved in these. And so I'm glad I did that. So we see that one, you know what I mean, wherever we plot the points, we can make a circle and we can be surprised that, hey, we're actually going to get quite a bit of shear. On this one, what are we going to get? Hey, we're going to double the shear. So the shear stress is going to be, the max shear is going to be probably double. The normal stresses aren't going to increase or decrease. We're not going to have too much more tension or too much more compression. But we are going to pick up this shear might be something on this diagram that we would have to look at. So yeah, so that's why I made this video, because it's just like, well, who the hell cares? Like, how much can these things increase or decrease by? So that's actually where I'm going to end the video, because that's kind of where I wanted to start it. It's just like, if I have any initial 3 values in the y, in the x, and in the shear, like, what's the worst case scenario? You know what I mean? Like, isn't it just a factor of 2? Like, that's what I thought. Going into this video is just like, well, I mean, does it really matter? I mean, because this is a lot of technical, this is very technical to get very specific numbers, which is cool, and it's good to check all this stuff, but it seems like, well, can't you just make it twice? Alright, hell yeah. So, I found my who cares moment. This is super cool. So, yeah, because I wanted the question, if you have, you know, these 3 values, like, can you just multiply by 2? And so, I would say no, because this could be a positive and this could be a negative. And, well, let's talk about that. I need to actually go down that rabbit hole. If this is twice positive and this is just once negative, then the difference between them is 3. And the shear is going to be 1.5. And so the normal stress and Oh yeah, that's fascinating. Oh, I gotta think about this. All right, hell yeah. So I've tried to come up with some examples, and we'll probably just end the video, you know what I mean, kind of with doing a few. I'm not definitive on this, so this is kind of like the, you know what I mean, don't trust me on this one. But if we have our initial sigma x and sigma y to be on these points, then our max shear is going to be halfway between them. So it's going to be the average of those. And wait, not the, it's going to be the, sorry, it's going to be the difference. So we're going to have the difference between them, but half the difference. I'm glad I caught that error. So the difference between these, so we're starting from here, this is big, this is this, and the difference between them divided by 2 is going to be this height. So that's going to be the max shear. And let's say, let's say our initial point was out here, sigma x, but then we also had some shear right here. Then I would say, hey, there is this half this distance between these, and so here's this point, and then here's this point. Here's the max shear. But what I'm going to say is, like, yeah, I have some sort of initial shear, but look at this. The initial shear is way bigger than the change. So I can just say, like, you know, so if I get a diagram where we have sigma x, sigma y, and then a shear, I can say confidently that the difference between sigma x minus sigma y divided by 2, you know, I mean, that's kind of the radius of this circle, or just it's just the halfway point, you know what I mean, between them. But I know this point is up here. I'm just going to say plus the initial sigma, plus the initial shear. I'm going to say this is shear max. So I'm overestimating, because I'm saying, hey, we're going to take this radius, and then we're going to add it to here. So I'm going to estimate my shear to be there, and I would be good. So that's what I wanted to do with this video, is just like, what are some take-homes where you're just like, I could never mess up, and I could see a problem. I'm going to take the difference divided by 2, add the shear, and then we'd be totally solid there. Here's a scenario where we have sigma x and sigma y are 0, but our shear, we for sure just have shear. And so in this one, you know what I mean? Hey, the difference between them goes away, and we just have the shear. And so we're good there. So here, as sigma x and sigma y get closer to each other, then this becomes really accurate. As sigma y and sigma x get farther apart, and we have a substantial amount of shear, so we can come up to, let's go up to this diagram. So if we have sigma x, sigma y, and then here's our shear, I'm going to say that we're going to say this max shear is this shear value plus this radius. And you can see that now we're totally overkill. But still, we can still use that. So as sigma x and sigma y get farther apart, finding the difference, half the difference, is that radius of that, plus the initial shear. This is, we're at least covering ourselves, because this is going to generate a bigger number. We're going to compare that to the strength of a material and shear. And cool. That's what I kind of wanted to do with this, because these Mohr's circle is so technical. It's good to just to have like some plays in your playbook. If sigma x and sigma y are the same, it doesn't matter where this origin is. The shear is going to be the difference. The shear is going to what? If sigma x and sigma y are the same, we're going to have a shear element, you know what I mean? So if we have sigma x, sigma y, and a shear, and these are the same values, this shear is going to be maxed out. So that's the other thing that is useful. This equation was trying to find max shear, and and that says, yeah, if these are the same, this goes away, and the max shear is just that initial value. Okay, so how would we find the increase in normal? You know what I mean? Because if my sigma x and sigma y are there, they are the maximums. But if I have sigma x and then the shear value, let's just come to here. How do I know, you know, and then down this, here is my maximum value. Well, I can still do that same thing. I can say if I have a sigma x or a sigma y, I can go plus or minus the shear, and this will be the sigma one. This will be the principal. I can just say these are the principal stresses. So if this is a big positive, I'm going to add it to here to get a bigger positive. If this is a negative, I'm going to subtract it from here to get a negative. And I'm going to say those, whatever one's bigger here is my principal, and then my second principal. And so I think that would work. So let's talk through that. So I could have a initial with an element where theta is 0, a sigma x, a sigma y, and a shear. And yeah, let's come all the way out to this one. And I'm going to say, if I'm on this part of the circle, here's the other point, and then here is my circle, and this is my maximum normal, and then this is my maximum negative. You know, so if my coordinate system for this one, my coordinate system's right here, so we actually get a pretty big max positive. This is going to be our second principal. This is going to be our first principal. If I said that this is just sigma x plus the shear, look at this. This is a big length, and that's always going to be longer. And so I can't think of a scenario where, you know, if I came out, so, you know, if this is my value right here, and it's associated, you know, this is my sigma x, this is my max sigma. So as the shear goes down, you know what I mean? Hey, and I'm adding that value, it's always overshooting. Now, if my sigma x is right here and my sigma y is right here, and I go to this part of the circle, cool. I'm going to add this length plus this radius, and yes, is this going to work out? Yeah, this would be my circle. This would be my max principal. And if I just said I'm going to take this initial sigma x plus this height, which is basically the radius. See how this is almost the full radius, and this is this much farther. So I'm going to go the full radius. I'm going to overshoot that. And even as sigma x and sigma y get closer and closer together, then I'm just going to add the shear. So that works. I mean, I don't know how to say this in words no more, but so the principal 1 and 2 for a guess is going to take sigma x or sigma y, plus or minus them. You know what I mean? You're going to make sure they get bigger in the positive or bigger in the negative, plus the initial shear, tau xy. And this is going to give me either sigma 1 or sigma 2. Cool. And then the other equation was, hey, we want to find the difference, sigma x minus sigma y divided by 2. And then we want to plus or minus that, because this could be a negative. This could be a negative or a positive number. And then we want to plus or minus this to the initial shear. And this will give us our max shear. And it'll be overshot or undershot. Hell yeah. I was thinking about putting this at the beginning of the video, but you know, it's not set in stone. Like I think I've proved that this will work. And in my wheelhouse, hell yeah, I love stuff like this. You know what I mean? Because this is the who cares perspective. So I can walk up to any problem now with with an element, usually at angle equals 0 degrees, have a sigma x, a sigma y, and a tau xy. And I can figure out what my maxes might be. And I can actually figure out both. I can figure out what my max principal and my second principal would be by plugging both of these in. Both are going to be overshots, but that's good because we want numbers that might have a little bit of a factor of safety. We would not want it the opposite way. And then to find the max shear, same thing. I can throw these into here. And yes, if there is no shear, the difference between these and half the difference between these is that radius. If there, and did I say that right? I said if there is no shear, yes, the difference, half the difference between these is that max. Now the other scenario is if these are the same. If these are the same, hey, this goes away, and this is my max, and we get perfectly accurate. And I think the other thing up here, yes, if we have this initial condition where we don't have any shear, and so this would be 0, then these are the maxes as well. That is the principal. And that's the definition of a principal. The definition of a principal axis is when your shear is 0. So it's just fascinating, like, saying that and not having the light bulb go on instantaneously. But hell yeah. So if I throw in a 0 value here, obviously that's the definition of principal. Whatever one's the biggest is sigma 1. Whatever one's the next is sigma 2. But I can have an approximation of what those principles might be, is if I just take those initials and then just, you know what I mean, add them or subtract them to get a bigger, if this is a positive and this is a negative, I'm going to add it to the shear. This one I'm going to subtract to the shear, and I'm going to try to get a big negative and a big positive. I'm going to see maybe which one's bigger, and then I'm going to call that one my principal and this one my second. Okay, sweet. So I think I am thoroughly done. And this week, you know, one of the questions is, like, when should you start teaching something? Is like the second, yeah, just go for it. I don't know. You know what I mean? Like, I've learned so much from this video that I wouldn't have just studying at the coffee shop. Like, everything helps. I mean, there are times where you want to do a coffee shop session. But this was cool. I did a 3-hour coffee shop session on the equations, the transformation equations, and then I did a 3-hour session, you know, talking my way through the textbooks, and then I did a 3-hour session going through the equations and trying not to make mistakes, and we did that. And then so I thought Mohr's circle was just the worst, but then actually, you know, just kind of reading what the Mohr's circle was, I was like, oh, I'm satisfied. Now I know what it is because I spent so long going through the transformation equations. But still, the only reason you would do Mohr's circle is so you can have a visual picture of what's going on. So I really do like the way I'm ending this video with these 3 take-home equations that overshoot and can be accurate if shear goes to 0. If shear goes to 0, they are perfectly accurate. If there is shear, it's an overshot. But still, material mechanics, again, we're trying to get the numbers for the stresses in tension, compression, and shear, and making sure those numbers aren't bigger than what the material can handle. Alright, hell yeah, and booyah.